Hello, welcome to Lab 4 Extreme Sports Ropes. Our task was to observe the motion of a mass oscillating on a spring and create a computational model to verify the energy principle. My results were the change in energy is approximately zero, as it should be. The change in X from the model to the experiment is approximately 22 centimeters, which is quite large and will be explained later. Here you can see the data and formulas that I used to make the model possible. Newton's second law was the major one, in which I had to find the final velocity first. So I used V initial plus the total amount of forces over mass times delta t. Then I had to find the final position, so I used the initial position plus the final velocity times delta t. Here the four total net forces are equal to the spring force and the gravitational force because those are the only ones that act on our system. The spring force is formula is given to us in the video as the constant of the spring times the value s and negative L hat. The formula for all three of these, which can be obtained in the video, are seen right here. Here, next I use the energy principle, which delta E is equal to the work done on the system by the surroundings, as in the potential energy and the actual change in kinetic energy. The systems that act on the surrounding systems that act on our system are the earth, gravity, and drag and spring, but we do not calculate for drag in our model. Therefore, the change in energy is equal to the change in kinetic energy, the change in potential gravitational energy, and the change in spring energy, which all equal to zero, as they should be. Here you can see the relevant data that I inputted into my VPython model. The mass given to us by the video is 0.402 kilograms. The initial position and velocity, which I extracted from my tracker data, is seen here. The spring data, as in the constant 6.12, and the relaxed length of the spring is seen right here, which I had to use the formulas given to me by the video in order to find out. And the time in which the whole experiment spans out, given to me by a tracker, is seen here as 9.307 seconds. Here I'm going to briefly scroll through my VPython as I've already shown you all the relevant models. You can see the formulas inputted here, and you can see everything that I showed earlier and how it's relevant once it's actually shown in the model. Now I'm going to run the model, and as I run the model, you will see the large differences in the code as I showed and said that we would discuss later. After a certain point, you can see that there starts to be a difference between the actual model and the experiment, and these differences are mainly due to the lack of the computation of the drag force and human error that may have been made slightly when tracking the points using tracker. Therefore, stated once again, the inaccuracy is shown due to lack of drag force, as you can see here. And if you look here as I run the model, you can see the motion of the two balls. This is the model ball, the blue one, and this is the actual experiment. You can see the model moves quite faster than the experiment, as the experiment drops quite lower than the model, which shows the difference in what should have happened and what the computer predicted to happen due to the lack of drag force. Now to answer the two "what does it mean" questions. The first one, is the energy principle satisfied? Yes. As shown by the model, the yellow line, it shows the total change in energy equaling zero, or approximately zero as it goes across the line. Furthermore, I had my code print the value of the energy principle, which can be seen here as 0.00014, or approximately zero, answering the question as yes. And finally, the second "what does it mean" question, to examine the oscillation periods that I have estimated for X and Y given to me by the tracker position. As you can see here, both of them start off with the same oscillation period of approximately 1.61, and Y keeps that one fairly constant, going throughout. At around here, it starts to switch between 1.61 and 1.62. 0.71. But that is a small difference. But as you can see that I showed you earlier, it caused a fairly large change. Now here, when it comes to the expositions, it also starts at 1.61. But by the time it gets here, it is moved up to 1.81 and continues to progress further and further as time continues, which shows why there is such a big difference between the model and experiment when they are compared to each other and the points are laid side by side. Thank you.